you should all have completed your observations for the squirrels, right?
Me and my partner haven't been able to get together.
What's that?
Me and my partner haven't been able to get together.
Okay, well, you need to do it quick. You ready? You got it? Okay, good. We want to analyze your data beginning this week, so it'd be good to get that taken care of. What I have on tap for today, I want to continue talking about competition theory. I want to get that out of the way. I don't mean to sound like it's not important. It's very important. But I would like, before we go to online, which is coming up third week of November. So we basically have 3 more weeks. I want to get the next little module, the lab module, taken care of, and that's the optimal forging stuff. Before I can talk about optimal forging, I need to talk about competition theory. All right, so what I'm going to do now is I'm just going to give you I'm going to just do a very quick overview, and then we're going to go into some competition theory, and hopefully you'll have a better understanding. Why do we have to know about competition theory? Because we also want to talk about predation theory. All right, I'm getting there. There's that one. Okay, we don't need to do that one. Which of these works? I was thinking about that. Okay. Very good. Okay. So we've already talked about Gauss's observations and this whole concept of the competitive exclusion principle, right? No 2 species can occupy the same niche at the same time. Now, what we want to do is we want to formalize that just a little bit. And what this is going to enable us to do is explain why it is that in some places you have lots of species, and other places you have relatively few species. So for example, consider lizards in Missouri versus lizards in New Mexico. Both states have roughly the same geographical area. One state is just a little bit farther south, the other state is just a little bit farther north. But otherwise they're very similar in their latitudinal and area considerations. And yet, if you look at how many species of lizards there are in Missouri, there are 10 species. There are 40 species at least in New Mexico, and you have to ask yourself, why is that? One way we can begin to understand that is by thinking about interspecific competition. Species diversity is in part a function of interspecific processes that are taking place. Okay? Now, if you go to the tropics, what you discover is that there are many more species. So we could look at these isoclines for species diversity, and what you discover is the farther north you go, or the farther south from the equator, the fewer species you have. The closer to the equator you get, the more species you have. And there are a number of reasons for that. One of the things that's happening though, right, as you go north, what's the obvious thing that's taking place? It's getting colder, okay, the winters become more severe. What does that mean in terms of the tolerance limits of species? The colder it gets, the more likely you are to exceed the tolerance limits of lots of species. So, and that happens both as you go towards the North Pole and as you go towards the South Pole. Now, think about how species respond. There are species at those northern latitudes. There are shrews, and there are mice, and there are these little tiny guys all the way up there close to the Arctic Circle. They are able to make it. What's different about them? Well, they've evolved all sorts of strategies for dealing with the cold, all sorts of strategies for getting through long periods without food, all sorts of strategies for all kinds of things. There is this general trend, as you go north, mammals get bigger. So on average, the body size of a mammal as you move north gets larger and larger and larger. So if you look at the average size of a mammal here in Missouri, it's probably 100 grams or something like that, relatively small. Most mammals are little tiny guys. We do have some bigger animals. We do have black bears, which are small bears. We do have cougars, which are largish cats. We have bobcats, which are small compared to lynx. Okay? So we have a few. We have white-tailed deer, which are small deer compared to mule deer or other sorts of deer. Okay? As you go north, what happens to the size of bears? Well, the biggest bears are the polar bears, followed by grizzly bears. A grizzly bear dwarfs a black bear. They're just monsters. If you look at the ungulates that are out there, we have white-tailed deer. If you've ever been next to an elk or a caribou, you realize how big those animals are. Even a mule deer is large compared to a white-tailed deer. So body sizes as you go north get larger. Why do you think that is? What's driving that? Well, obviously something with temperature. What happens as you get bigger?
You retain more heat.
Pardon?
You retain more heat.
You retain more heat. It's all about surface area to volume ratio. When you're small, you have a high surface area relative to your volume. When you're large, the surface area compared to the volume is much smaller. Your volume increases as the cube. Your surface area only increases as the square. So area is something times something. Volume or mass is something times something times something, right? So one increases as the cube, the other increases as the square. The same phenomena applies to people, right, and their ability to gain weight or lose weight. When you were in high school and skinny as a rail and desperately trying to put on weight, it was very hard because you had such a high surface area compared to your volume. Most of the calories that you took in were being lost as heat. Once you've packed on 100 pounds or 200 pounds, the surface area compared to your volume is much smaller. And now, relatively little of your heat is being lost to the environment. Most of it is being retained. So your caloric demands, right, on a per gram basis are actually less. Years ago, there was an interest in switching over from cattle to bison in this country. And there are some restaurants that will sell bison burgers. The Buckners, before its last incarnation, you could actually go down there and buy bison burgers, and they were okay. They were not as tasty as some that you would get out west, but they were okay. Why would they be interested in raising bison? Well, a bison is a much bigger animal than a cow, right? I mean, a lot bigger. And what that means is the per gram energy that it needs to take in is less than what a cow needs to take in. the per gram energy that a mouse needs to take in is enormous compared to what a cow needs to take in. So the bigger the animal, on a per gram basis, the less you have to feed it. That's the basic principle. All right, so let's then look and compare something like the tropics with something like the temperate zone. So here we are, right? And in this same relative resource availability curve, so this curve right here, those are the resources that are available. Each of these curves down here is the niche or the resource utilization curve. Here we're able to pack in 3 species. In the same relative resource availability curve, in the tropics you get 1, 2, 3, 4, 5, 6, 7, 8, 9 species. So 3 times as many species. What's different? Well, here's the distance from one species to the next. It's that much. Here, the distance from one species to the next is much smaller. So the species here are packed much more tightly than they are here. Okay? So that's one observation. Why is that? Why are the species here packed so loosely? One answer is the fact that here in the temperate zone, this resource availability curve is unpredictable. Every year is different from the previous year. If you've worked on a farm or lived on a farm, you understand that. Some years, it's good for soybeans. Some years, it's awful. Some years, you can't get into the field until really late. Other years, you get in right away. Okay? Some years, it's hot and dry. Other years, it's cool and wet. One of the things about living in the temperate zone is that the amplitudes of temperatures, yearly and daily, are unpredictable compared to the tropics. In the tropics, it's basically the same one year to the next. 1 month to the next, 1 day to the next. We dealt with that in the first part of the semester. So in the tropics, this curve right here is very predictable. In the temperate zone, that curve is not very predictable. The result is, if this curve is unpredictable, and you're a species living under that curve, relying on those resources, you'd better be able to have something to eat when your preferred food item goes away. So if suddenly this curve on 1 year drops down like this species right here now has lost most of its resources. It better be able then to shift a little bit and exploit these resources over here. In other words, the niche for each species has to be wide enough so that even if on some years some of its resources are not available, it will have other resources that it can exploit. So as the environment becomes less predictable, the niche for each species has to become wider, broader, so that it has something that it can exploit. In the tropics, where everything is very predictable, it's possible for the niche to be very narrow. We have a term for that. In the tropics, species tend to be specialized. In the temperate zone, species tend to be generalists. So when resources are highly predictable, you can be specialized. When resources are unpredictable, you have to be a generalist. What are people? We're generalists, right? We're good at doing a lot of things reasonably well. There's not one thing that we do exceptionally well. Compare that with some species that are insanely good at what they do, like a cheetah, right? Which is insanely good at running down small prey items and killing them, okay? Or think about these wasps that parasitize cockroaches. So it's able to land on the cockroach, neutralize the cockroach, paralyzes the cockroach, deposits its eggs inside the body of the cockroach, keep the cockroach alive, and then the eggs develop into larvae and basically consume this living cockroach from the inside out, not killing it until they finally emerge as new wasps. Isn't that cool? That's this highly specialized kind of a thing. That's the sort of thing you can do when the resource is highly predictable. There's another component to all of this, and that concerns this overlap between the species. So here, the overlap between any two species is really large. Here, the overlap between any two species is smaller. So one of the things that happens in the tropics is that the overlap between species is less. In the temperate zone, the overlap between species is greater. That overlap is an indication of how much competition there is in the system. The less overlap, the less competition. The more overlap, the more competition there is. Same thing with fast food restaurants. What are fast food restaurants trying to do? Distinguish themselves from all the other fast food restaurants. They're trying to minimize the amount of overlap, the amount of competition with other fast food restaurants. That's why McDonald's and Burger King fine-tune their menus, right, and their dining experience so that they're overlapping less and less with the other restaurant. That amount of overlap is an indication of the amount of competition. What's the result of natural selection? Natural selection should result in a reduction in the amount of competition. So here in the tropics, these species have coexisted for a long time, and natural selection has reduced the interspecific competition between species, and the result is that the species are now specialists. Here, the system is unpredictable. The species have a shorter shared evolutionary history. Natural selection is reducing the amount of overlap, but clearly not to the extent that you see in the tropics. So what I want to do now then is, well, let me just give you a couple of clear examples of what the effects of competition have been. Let's look at the finches that are on the Galapagos Islands. The Galapagos Islands, as you probably know, are close to the equator, and they are oceanic islands off the coast of Ecuador. So they're oceanic islands, not on the continental shelf. So they're way the heck out there. And if you go to the Galapagos, if you're ever lucky enough to make it to the Galapagos, hopefully not on a cruise ship, okay, or one of those ridiculous sorts of things, but if you can actually go there on an internship or spend time on the, as a biologist out on the Galapagos, it is absolutely amazing. One of the things that you notice is there are these lizards out there, and you ask her, these marine iguanas, where the hell did those marine iguanas come from? How did they get there? What the hell is a marine iguana anyway? Well, it's a large lizard, right? And big lizards tend to be herbivorous. They eat plants. They don't eat, with the exception of things like savanna monitors and that sort of stuff, they eat plants. Who's their closest evolutionary relative to the marine iguanas? Green iguanas, which are all over Ecuador. So, in other words, marine iguanas evolved from the green iguanas. How did marine iguanas get there? How did they get to the Galapagos Islands? That must have been the 8th day of creation. God goes, oh yeah, forgot. Hey, this will be cool. Let's take some green iguanas and put them over here and change them a little bit. How did they get there? Well, what do lizards do? Well, living in the Midwest, it's hard to know, I suppose. But if you've ever been out west and you've watched lizards, you know that one of the things that they do is they bask. Okay? They find a nice sunny spot and they bask. And that's especially true for iguanas because they have this plant-based diet and it's hard to digest cellulose. So they bask in the sun and they get their body temperature really high, and that enables them to ferment all of the cellulose that's inside their guts. So they're dependent on that fermentation. So they're basking. And it's pretty easy to imagine, because of the behavior of marine iguanas, there's some nice log washed up on the beach, and there's a green iguana climbing up on the log, basking, warming itself. The tide comes in and the log washes out. And the current takes that log and takes it straight to the Galapagos Islands where it washes up on the beach again. Might take several weeks for him to get there, but he's a lizard, so it's fine. Because lizards don't have to eat every day. They can actually go quite some time between meals. So he washes up on the shore in the Galapagos, and hey, there are already some other green iguanas there. What's there to eat? The Galapagos Islands are barren, desert-like islands. There's no lush vegetation there. So what are these green iguanas going to eat? Well, what's available? In the surf is seaweed and algae, kelp, okay? So what these iguanas have done is they've developed the ability to go into the water and harvest the algae. And then they climb out of the water and they go up on the rocks and cling to the rocks and sun themselves on the rocks. And over all the eons that they've been there, they have accumulated sufficient differences so that now they are functionally very different from green iguanas. Same thing happened with finches. Although finches, it's much easier to get out there. All you need is some big storm, or hurricane, or typhoon, or something like that. And a species of finch gets blown out to the Galapagos, and once on the Galapagos, right, it has food available to it. But what happened to the Galapagos finches that started off with one species, and over time there were several speciation events so that now you have multiple species and they've specialized. This guy right here has a very small beak and it's specializing on little small seeds. This one has a very big beak and it's specializing on very big seeds. So they've subdivided the resource availability curve. You've speciated into multiple different species. And you have guys with little beaks, medium beaks, and big beaks, and they're all taking different food items. So their niches have become separated. They still have some overlap, but natural selection is operating to reduce the amount of overlap. All right. So, there we go. Let's go through these models, okay? We now want to do a little mathematical modeling and figure out if we can understand how competition works and the conditions under which two species can be expected to coexist. Okay? Easy. I know, how many people have had calculus? Anybody? Okay, so nobody here has had calculus. That's fine, no worries. You don't need calculus. All you need is a little bit of algebra, okay? Because these models right here, we did this before, right? If you look at that part of it, just right there, forget about the subscript 1, that's our exponential growth model, is it not? Yeah. dn dt equals Rn. So change in population size of species 1 relative to time equals the growth rate of species 1 times the population size of species 1. That's just exponential population growth. And we have 2 species, so we have 2 equations. So we have species 1 and species 2. Now the beauty of differential equations is that in this case, there is no explicit solution. In other words, you cannot solve that equation and get the exact answer. That's true probably for most differential equations. The wiring system, the electronic system in this building was designed using differential equations. The electronics in your car was designed using differential equations. The plumbing system in a big industrial complex is designed using differential equations. Okay? Bridges are built using differential equations. And most of the time, you can't solve the differential equation. Doesn't matter. You don't have to solve it. All you need to know is what the behavior of the equation is. And we know enough about how the system works to be able to understand that behavior, and that's what I'm going to show you how to do. So let's look now at the second part of this. If I subtract this part right there, well, that is our logistic growth equation from before, right? So, except we had 1 minus n1 over k. Well, that's the same thing, okay? Because k1 divided by k1 is 1. So just forget about that part of it. So in a logistic sense, the growth of species 1 is dn dt equals Rn times 1 minus n over k. There it is. And if n is larger than k, then the population is going to decrease. If n is equal to k, it stays the same. If n is less than k, then the population is going to increase. And we're doing that for both species. So what we're modeling here is the growth of 2 different species. What we've done is we've added a term here on the back end of each equation. And that term is alpha 1, 2 and alpha 2, 1. So here, the growth of species 1 is equal to R times n, 1, plus 1 minus n over k, fine, minus alpha 1, 2 times n2. So minus some proportion of species 2. Minus some proportion of species 2. If this is species 1, and that's species 2, there's the proportion of species 2. Okay? So that, right there from species 2, is actually using the same resources that species 1 is. So species 1 is using that, but species 2 is using that as well. So if I want to look at, has the species reached its carrying capacity? Well, species 2 is reducing the carrying capacity at the same time that species 1, or species 2 rather, is consuming the resources at the same time that species 1 is. So they're both serving to reduce the carrying capacity. All right. Here I have alpha 1, 2. Here I have alpha 2, 1. Why is that? What that alpha represents, that alpha is referred to as the competition coefficient. So alpha 1, 2 is the competitive effect of species 2 on species 1. Alpha 2, 1 is the competitive effect of species 1 on species 2. Shouldn't they be exactly the same? No. Let me show you why. I'm going to turn this off and do the next bit on the board. Here we have two species. There's species 1. There's species 2. Species 1 and species 2. Alpha 1, 2 is the effect of species 2 on species 1. So alpha 1, 2 is that as a proportion of that. So this area divided by that area is what? 20%? Okay, roughly. That area divided by that area is roughly 20%. Now, alpha 2, 1 is that area divided by that area, which is perhaps 5%. Okay? So this is small compared to all of this. This is relatively large compared to that. So the competitive effect that species 2 has on 1 is large. The competitive effect that species 1 has on 2 is relatively small. In other words, alpha 1, 2 does not necessarily equal alpha 2, 1. That's important. All right. So we cannot solve these differential equations. Let's write them down. We have dn1 dt equals r1 n1 times k1 minus n1 minus alpha 1, 2, n2 divided by k1. And we have dn2 divided by dt equals r2 n2 times k2 minus n2 minus alpha 2, 1 n1 divided by k2. All right. Notice k1 is not the same as k2. The carrying capacity for one species is not necessarily the same for the carrying capacity for the other species. They might be different. We can't solve those equations. Not possible. Try as you might. Whatever algebra you want to do, whatever transformations you want to do, however you want to approach it, you're not going to solve those equations. So the best we can hope to do is understand the behavior. So the first thing let's do is let's find the equilibrium point. That's probably the most interesting place to look. What does this look like when these two species are at equilibrium? What does it mean when they are at equilibrium? It means that the two species are coexisting. So what are the conditions necessary for coexistence? It's the same as asking, what are the conditions necessary for equilibrium? Great. Tell me, where are these two species in equilibrium? Well, what approach should you take? How do we find out? How do we get there? What happens in equilibrium? What do we mean when we say a system is in equilibrium? Okay. You get in your car, you turn it on, pull up to a stoplight, it's idling, light turns green, you step on the gas. Is the car at equilibrium? Is the engine at equilibrium? No, it's not. It's accelerating. It's going faster and faster and faster and faster and faster. Now, you pull over to the side of the road, you stop, put it in park, let the engine idle. Is it at equilibrium? Everything is static. Nothing is changing. The RPMs is the same, fuel consumption rate is the same, oil temperature is the same, oil pressure is the same, right? Engine temperature is the same, everything is not changing. Is it at equilibrium? Yeah, because nothing is changing. At equilibrium, it's not changing, it's static, it's staying the same. So, where is equilibrium? This is simple algebra. I have two equations, all right? I want to know, where is my equilibrium point? Well, what should I do? I know that equilibrium is when the system doesn't change anymore. So when does the system not change here? So, sometimes there's this really telling thing that happens when people start talking about the coronavirus. And President Trump makes this big deal about how he's a very stable genius and how he's very smart. And he claims that the only reason we have so many of COVID-19 cases is because we do so much testing. And it is true that the more you test, the more COVID-19 cases you will find. But testing less doesn't make the COVID-19 virus go away. Whether you test or not, the virus is still there. And that's an intellectual leap that he is unable to make. He can't figure that out. He thinks, test more, you get more virus. And that's not true. Okay? Sometimes it's really simple, and yet some people are unable to see it. And that's the value of an education, is your ability to see something and right away recognize, right, the causality of what's going on. He's not there. In other words, on that Bloom's, cognitive, taxonomy thing, he did not make it to formal operational thinker. So all I'm asking you now is, look at these two equations. When are they at equilibrium? What is the very first step? What is the definition of equilibrium? No change. What's the left-hand side of that equation say? On the left-hand side of the equal sign, what does dn dt mean? What's the algebraic version rather than the differential equations version? Let's rewrite dn dt. How would you write it? Delta n over delta t. What does delta mean? Change. I'll be dipped in shit. There it is. So, if delta n delta t, if there's no change, what does delta n delta t equal? Pardon?
1.
No.
0.
0. When delta n over delta t is equal to 0, you have no change. If delta n over delta t is equal to 1, you still have change. The change is 1. So now, bingo. You now know that at equilibrium, 0 is equal to that, and 0 is equal to that. Great. We've got two equations. We've now made the first step. Let's simplify those two equations. What should we do? They're too messy, too much stuff there. I want them simpler. It's always a good strategy. Keep it simple. All right? Simplify it. Let's simplify those equations. What could we do to simplify those equations? And all I'm asking you is to think back to 3rd grade algebra. How could you simplify it? I'm asking you to make a cognitive leap that is unavailable to your president. He might be a good guy, I don't know, I don't care, okay? But I'm asking you to outthink him. All you want to do is make it simpler. What algebraic operation could you do? What could you do to both sides of the equation so that we have less stuff up there?
Divide.
Divide by something? What do you want to divide by?
Divide by the R and N.
Damn. See? You should run for president. Okay? Awesome. Divide both sides by Rn. 0 divided by Rn is what? 0. If I divide this term by Rn, I get rid of that. And I'll do the same thing down here. Sweet. That already looks much better. They're still too complicated.
Get rid of the K.
Multiply both sides by the k. Multiply 0 times k2, I get 0. Multiply 0 times k1, I get 0. Multiply this side by k1, and I get that. Multiply this side times k2, and I get that. Awesome. Now, let's add n1 to both sides of the equation over here. So 0 plus n1 is n1. And this plus n1 is this. And then the same thing here. Here I'm going to have n2. All right? Now that wasn't so hard, was it? All right. What is that? The equation of. What does that look like? You've seen it before, man. You saw it in, if not in 3rd grade algebra, you saw it in 4th grade algebra. What is that an equation of? We've got two things that we're interested in. we're interested in N1, and we're interested in N2. All the other stuff is just kind of stuff. So what we're saying is that N1 is related to N2 in this way. So now what is that the equation of? That's N1, and that's N2.
Just a line?
It's a line, right? Isn't the line y equals ax plus b? Isn't that the equation for a line, or mx plus b, or however you want to do it, okay? And what is a? That's the slope. And what is b? That's the intercept. So here you have n equal, well, k must be the intercept, and a12 must be the slope. So it's the equation of a line. So I have two equations of lines. I'm going to move these over here a little bit. So I've got n1 equals k1 minus alpha 1, 2, n2. I've got n2 is equal to k2 minus alpha 2, 1, n1. So here's species N1, and here's species N2. So we're talking about a system of two species. We've got species 1 and species 2. All right? The two species are coexisting. They're at equilibrium. The system is stable. At what point, where is the equilibrium point for these two species? Well, there are two species. So we have one line for species 1 relative to 2, and another one for species 2 relative to 1. So let's put those two lines in. Okay, where's the equilibrium point?
The intersection.
Right there. That's the equilibrium point. That's where the two species coexist. So here is dn1 dt, and here is dn2 dt. All right, now the question is the equilibrium stable? Or is the equilibrium point unstable? If the equilibrium point is unstable, what that means is that if there's a perturbation to the system, if we move it away from the equilibrium point, is it going to return to the equilibrium point, or is it going to go somewhere else? That's the question. So imagine you're looking at the equilibrium between white-tailed deer and mule deer in the Black Hills of South Dakota. And somebody goes in and poaches 100 mule deer. You've now displaced this equilibrium point. Is it going to return to its equilibrium point over time, or is it going to cycle to the extinction of the mule deer? That's what we want to know. So what we're asking is, what are the conditions necessary for equilibrium, for a stable equilibrium? Is that equilibrium point stable or is it unstable? Well, how can we figure that out? Well, what we want to do is two things. First of all, let's figure out what the endpoints are here. Let's figure out what that is, and that is, and that, and that. Let's figure out what those things are. Let's start off with species 1. How can we find that point right there? Well, easy. If this is species 1, okay, when species 1 is equal to 0, how many species 2 are there? Well, when species 1 is equal to 0, then I have 0 equals K1 minus alpha 1, 2, and 2. Okay? So now that means that K1 is equal to alpha 1, 2, N2. Divide both sides by alpha 1, 2. So I know that when N1 is equal to 0, then N2 is equal to K1 over alpha 1, 2. So this is the point, K1 divided by alpha 1, 2. Everyone see how I got there? Yeah? Or not? If you don't understand it, let's make sure that you do. All I've done, here's the line for species N1. There's my equation for species N1. I want to know what that intercept is right there. Well, that happens when N1 is equal to 0. So I'll put 0 into this equation. Take this, add alpha 1, 2 to both sides. So then I get this equation right here. Divide by alpha 1, 2 on both sides. And then I know that N2 is equal to that. It's just algebra. What's that point right there? Well, that happens when N2 is equal to 0. So let's take this equation for species 1 again. N1 is equal to K1 minus alpha 1, 2 times N2. But if N2 is equal to 0, then that's simply K1. So this is K1. Now let's do the same thing for species 2. Here's the equation, the line for species 2. What's this? For species 2, that's when N1 is equal to 0. When N1 is equal to 0, then N2 is equal to K2. So that's K2. When N2 is equal to 0, then I have 0 equals K2 minus alpha 2, 1, N1. So alpha 2, 1, N1 is equal to K2. Divide both sides by alpha 2, 1. That cancels out. So N1 is equal to K2 over alpha 2, 1. K2 over alpha 2, 1. All right. Is it stable? Well, let's see. Imagine we have a point right there. We've perturbed the equilibrium point to there. That's species 1. This is species 2. Here's the axis for species 1. There's the isocline. That's the isocline. All right. Species 1 is below its isocline. It's going to increase. Species 2 is below its isocline, so it's going to increase. If you're below your isocline, you increase. If you're above your isocline, you decrease. This is called a phase plane analysis. This is what we're using to understand the behavior of this system. We can't solve it, but we can study the behavior using a phase plane analysis. So here I have two vectors. And you remember from your physics class, if you took a course in physics, that the resolution of those two vectors is that. So in other words, if I perturb it to here, I'm going to move in that direction. Let's go up here. Imagine the equilibrium point gets perturbed up to that point. What happens to species 1? Species 1 is going in this direction. Species 1 is below its isocline, so it increases. Question?
What's the isocline then?
The iso means the same. So on this line, that's where species 1 stays the same. And on this line, that's where species 2 stays the same. If you're below your isocline, you increase. If you're above it, you decrease. Species 1 is below its isocline, so it increases. It increases along the n1 axis. Species 2 is above its isocline, so it decreases. Species 2 is going in this direction. So the resolution of those two vectors is that. Let's imagine we end up right here. Now, species 1 is above its isocline, so it decreases. Species 2 is below its isocline, so it increases. Now let's imagine we're a point right there. Species 1 is above its isocline, so it decreases. Species 2 is above its isocline, so it decreases. So it's going like that. So if we did that for thousands of points over all this graph, where would all those arrows point us? Toward the equilibrium point. So all these arrows are taking us back to the equilibrium point. In other words, under these conditions, we have a stable equilibrium. All right? So the system is stable. So what are the conditions that we have under these circumstances? What we have is K1 over alpha 1, 2 is greater than K2, and K2 over alpha 2, 1 is greater than K1. All right, what does that mean? That's the alpha, okay? So if the carrying capacity for species 1 relative to alpha is greater than the carrying capacity of species 2, and the carrying capacity of species 2 relative to the effect of species 1 on species 2 is greater than the carrying capacity of species 1, then you can get stable coexistence. So it's not just the carrying capacity, how tall that curve is, but it's also the relative size of that alpha. Okay? Let's flip these axes and see what happens. Now I'm going to take let's see, before I had this was species 1. Now I'm going to make that species 2, and I'm going to make this species 1. Okay? Let's repeat the analysis. So we flipped those axes. Let's repeat the analysis. Let me leave this there. So I'm going to put stable. Okay? Let's see. Here's species 2, right there. Let's start with species 2. What's that point? That point right there is when n1 is equal to 2, n1 is equal to 0. So when n1 is equal to 0, then n2 is equal to k2. So this then is k2. And this point right there is when n2 is equal to 0. So that is equal to 0, which then means that k2 equals alpha 2, 1, n1. Divide both sides by alpha 2, 1. To have k2 over alpha 2, 1. Now, let's do this one. That's species 1. So what happens when n1 is equal to 0? Then I have that. So then I have alpha 1, 2, n2 is equal to k1. Both sides by alpha 1, 2. So that means this point is k1 divided by alpha 1, 2. And then that point right there, that's going to be when n2 is equal to 0. Then I have n1 equals k1. So now, what I've done is I've taken these inequalities here and flipped them. Is the system stable? Let's look at, there's our equilibrium point. Let's start off down here. So species 1 is below its isocline, so it increases. Species 2 is below its isocline, so it increases. So we're going off in that direction. Both species are above their isoclines, both species decrease. So we're going off in that direction. Now let's go here. Species 1 is above its isocline, so species 1 decreases. Species 2 is below its isocline, so it increases. Now we're going off like that. Here, species 1 is below its isocline, so it increases. Species 2 is above its isocline, so it decreases. So we're going off like that. So you end up either there or there. So if the axes are flipped like that, and you're perturbed away from this, you're going to end up either there or there. So that equilibrium point is not stable. All right? So if you're perturbed and you cycle away from this, you're going to go to either one of those other equilibrium points. That equilibrium point is stable, but in this system, there's only one species. In this system, there's only one species. The two-species system does not persist. Any perturbation results in extinction of one of the species. All right? So that's the mathematical formulation of the competitive exclusion principle. And the question is, what are the conditions necessary for stability? And the answer is right here. There are two sets of conditions necessary for stability. This set of conditions right here is referred to as K compatibility. Okay, that's the first set of conditions. The second set of conditions is alpha compatibility. And alpha compatibility says this, and that is that alpha 1, 1 is greater than alpha 1, 1, alpha 1, 1 is greater than alpha 1, 2, alpha 2, 1, and alpha 2, 2, alpha 2, 2 is greater than alpha 1, 2, alpha 2, 1. In other words, alpha compatibility says that intraspecific competition is greater than interspecific competition. So those are the two conditions necessary for coexistence of species. Alpha compatibility and K compatibility. What does alpha compatibility say? It says that intraspecific competition must be greater than interspecific competition. In other words, you and I compete with each other for access to resources more strongly than we compete with mice or cows or oak trees or cockroaches. All right? That makes sense. K compatibility says that the carrying capacity for one species divided by the competitive effect of the other species on it must be greater than the carrying capacity of the other species. And the same is true for the second species. So there's this guy named Francisco Ayala. I think he was from Stanford. And this was back in the days when all of these models were first being developed. These models were being developed by a guy named Robert MacArthur, who was out of Princeton, and he was a good-looking guy, came from a family with a lot of money, and he had the extreme good fortune to die very young, so that he became a god in the ecological community. Because he was smart and wealthy and good-looking and all of that sort of stuff, and he dies. So all of his work sort of becomes enshrined in the ecological literature. There's this guy, Francisco Ayala, so this Hispanic guy out at Stanford, and he looks at that and he goes, well, that's sort of amusing. Let's do a little experiment and see if it's true. So he gets 2 species of fruit flies, and he sets up these experiments where he has competition ongoing between these 2 sets of fruit flies. And he repeats the experiments again and again and again and again, and he does all of this stuff. He estimates the carrying capacity and the competitive coefficients and all that sort. He does all that stuff, and it never works. And he writes this paper that gets published in Science, and the paper is titled Invalidation of the Competitive Exclusion Principle, which is a nice way of saying this is all bullshit. Okay? And everybody's all got their knickers in a twist, you know, because this has become the dogma of how the system works. And somebody finally looks at what Francisco Ayala did, and they try and figure out why is it that it didn't work in his system. And they made this interesting determination. And it's important, because let's go back and think about what we've really done here. We've taken a differential equation that looks like this. Okay, minus the competitive effect, right? So minus alpha times the other species, alpha 1, 2 over k, like that, right? So that's what we've done. What's the shape of that equation? The shape of that equation is like this. Okay? Great. It assumes that populations grow in a logistic fashion. The question is, do populations really grow in a logistic fashion? Well, in this class, we talked about a different kind of equation called the Renewal Equation, where population growth was instead modeled by births to females at time t, right, is equal to g at t, plus the sum of births to females at time t minus x times mx lx, right? If you model using this more realistic approach right here, you don't get exactly this behavior. You get something else. Similar to that, but not exact. Okay? In other words, what Ayala did, he assumed that the carrying capacity was a constant, and he assumed the population grew logistically. In the reanalysis of Ayala's work, what they discovered was that these isoclines are not really lines. In fact, they look more like this. They're curves. So what Ayala was doing is he was saying, oh yeah, they're lines, and that means the equilibrium point is out here somewhere, whereas in fact, the equilibrium point was out there. And when they did the adjustments for the shape of his isoclines, suddenly the system worked yet again. In other words, this whole analysis that we've gone through, it's not exact, but it does give you a sense of the behavior of the overall system. And what's important is this part right here, alpha compatibility, and this part right here, the K compatibility. If we want to understand are 2 species able to coexist, we need to first establish, do we have alpha compatibility? And second, do we have K compatibility? And then we can get a rough idea. There is one very important part of this, and I want to talk about that just very briefly. And that is this. We say that for competition to work, resources must be limiting. You can go into the literature and start reading papers that have titles that read something like competition between this and this, competition between that and the other thing, competition in this system, competition in that system. Read all those papers and search all of those papers for where they demonstrate that the resources are limiting. And they never do that. Nobody ever demonstrates that the resources are limiting. Ultimately, all the models that we're talking about here, MacArthur gets the credit for those models, but where do they really come from? Business. Everything we're talking about comes from business. Well, in business, it's easy. You know what the resource is. The resource is the wallet in the back pocket of your customer. Okay? And all you're trying to do is harvest it. If you're deciding, where am I going to put my new fast food chain restaurant, that's the analysis that you're doing. You're trying to squeeze your restaurant in between Burger King and McDonald's or something like that. It's pretty straightforward. But now, when we're talking about a natural system, is the resource limiting? First thing you have to understand, what's the resource that's potentially limiting? And second, even now, once you understand what that resource is, can you now exploit it? Can you determine whether it's limiting? If you were in political science, running a presidential campaign, you could think of the voters as being a resource. You're trying to secure those voters, right? And the alpha, the overlap, right, that competition coefficient, that's where you need to expend your effort, right? Is it possible you don't want a stable equilibrium, you want to drive the system to the extinction of the other voter, right, the other candidate. You want to drive the other species, the other party to extinction in this particular election. It would be an awesome PhD dissertation in political science to do that sort of modeling. That would be fun. All right. Nobody ever demonstrates that resources are limiting. What does that mean for us then? What it means is we have this basic understanding of interspecific competition. We know what natural selection is doing. We know basically how the system should work. But we find ourselves in a situation where it's almost impossible to demonstrate it. You know that it's there, but you can't really demonstrate it. It's a little bit like in physics, right, where Einstein has all these predictions about how the system works, and you can't really do anything with it because you don't have the ability to measure the sorts of things you need to measure in order to get there. Okay? All right. All right, so there's this this guy, G. Evelyn, a very 50s-ish kind of a name, Hutchinson. G. Evelyn Hutchinson gave this paper at the annual meeting of the American Society of Naturalists. The American Society of Naturalists was a professional society that was founded by Edward Drinker Cope. You guys know who Edward Drinker Cope was? I think we've talked about Cope a little bit, did we not? Did we talk about Cope and Marsh? Othniel Charles Marsh and Edward Drinker Cope. Those are the two giant names in vertebrate paleontology. Those two men are responsible for 95% of what we know about dinosaurs. They lived in the 1800s. They started off as friends and became bitter enemies. They both were wealthy. They were both very sharp and very bright. Edward Drinker Cope died relatively young. He didn't even reach 60. He had published 1,600 scientific papers in his life. That's a record that wasn't surpassed until a few years ago by a guy named Hobart Smith, who published at the age of 93 his 1,601st paper. To give you a sense of what that means, if you were to ask the average CMO faculty member in biology, how many papers have they published? It's a little bit better now than it was in the past, but when I first got here, in their professional career, the average CMO faculty member in biology would have published one paper. That was the requirement for making full professor. You had to publish one paper. Now it's probably closer to 20 papers or something like that. Publishing a paper when you're also teaching is hard, right? If you can get one paper out every year, you're doing great. Some faculty members do better, some do worse, okay? Marsh, on the other hand, at the end of his career, published 400 papers. So 25% of what Cope did. Marsh, his uncle was George Peabody from Peabody Coal. And George Peabody funded his lifestyle. He didn't graduate high school until he was in his 20s. It's because he liked the ladies, and he liked booze, and he liked to party. He did graduate, he went to school at Yale. He did graduate with a bachelor's degree at Yale. And he convinced his uncle to make a large donation to Yale, and he did. And that donation was used to create the Museum of Vertebrate Paleontology at Yale. And part of that donation was the stipulation that they hire O.C. Marsh as the curator of paleontology at Yale for the rest of his life. And they did. And they paid him a salary of $1 a year, which was fine because he was independently wealthy. Edward Drinker Cope, his father was a Quaker, and Quakers as a religious group were interested in natural history. Richard Tricky Dick Milhouse Nixon, who was impeached, or who was not impeached but resigned his office rather than be impeached, was a Quaker. And interestingly, Nixon, as a despicable person as he was responsible for a lot of the environmental regulations and whatnot that we have today. So that's because of his interest in the natural world. At any rate, Edward Drinker Cope was doing field work in the Dakotas and got along really well with the various Sioux tribes that he came into contact with. O.C. Marsh, when he went into the field, went out with the cavalry and was involved in the slaughter of many, many thousands and thousands of bison, as well as the slaughter of Indians and so on, so that he could do his field work. Whereas Edward Drinker Cope worked with the Indians, O.C. Marsh and his teams battled them. One of O.C. Marsh's field members once murdered some field members from Edward Drinker Cope. Edward Drinker Cope reciprocated by stealing a train full of fossils that had been dug up by Marsh. these two people hated each other. They both died poor and in ruins, and neither one, they both lost the entirety of their collections to various. One just interesting little side note, Edward Drinker Cope, late in his life, realized that there was no type specimen for Homo sapiens. And he hated Marsh so much that he stipulated in his will that after he died that the brain volume of his skull should be measured and compared to that of O.C. Marsh so that he could demonstrate once and for all that he was smarter than Marsh. And because this was at the time when people thought that a large brain was also a smarter brain. Right? And he also stipulated that his skeleton be used to describe the type specimen or become the type specimen for Homo sapiens. Well, he died in the 1800s, and it wasn't until, I guess it was about 15 years ago, that, interestingly, a student in the Vertebrate Paleontology Museum at Yale, working under Ostrom, who occupied the seat that was once occupied by Marsh, one of Ostrom's students made this little discovery about the will of Edward Drinker Cope. So they got the skeleton of Edward Drinker Cope, which had been in the Philadelphia Museum, and they wrote the paper describing the type specimen for Homo sapiens. They submitted the paper, and then they took Cope's skull on a world tour. So they built this very special, beautiful box, right? They put the skull in there, and they traveled the world to all these museums showing off Cope's skull as the type specimen for Homo sapiens. So that was Cope's ultimate revenge over O.C. Marsh. But ultimately, the paper was rejected. So they were not going to use his skull as a type specimen for Homo sapiens. And the reason was simple. When you submit a type specimen, the specimen must be perfect. No missing teeth, no broken bits, right? It has to be perfect and complete. And Edward Drinker Cope had false teeth. And the fact that he had false teeth, number one, enabled him to become friends with the Indians, because when they'd sit around in the campfire, the Indians would come and sit around his campfire with them. And the reason they came was because they wanted to watch him take his teeth out and play with his teeth. The Indians thought that was hilarious. So that enabled him to have a good relationship with the Indians, but at the same time, it prevented him from his ultimate revenge, becoming the type specimen for Homo sapiens and displacing Marsh. The final insult for Cope was this. He founded this journal called The American Naturalist. O.C. Marsh founded a journal called American Men of Science, which folded after 1 year. Edward Drinker Cope's journal, The American Naturalist, is the premier journal in ecology. The Herpetological Society has a journal called Copia, right? It's not just the Herp Society, but it's Ix and Herp, so ichthyology and herpetology, called Copia. And that society just voted this year to change the name of the journal from Copia to something else. So they've gotten rid of Cope's name from the journal. And the reason they've done that is because Edward Drinker Cope was both a sexist and a racist. Back in the 1800s, you would be hard-pressed to find anybody that was not a sexist and a racist. Benjamin Franklin was a racist. Benjamin Franklin wanted all the forests cleared to let the light in so that we wouldn't have the darkness. And then in his papers, he writes directly about blacks and how you don't want that, how the blacks are inferior. Even Lincoln thought the blacks were inferior. And Lincoln's plan after the Civil War was not to open up the country to blacks, but instead to send them back where they came from. That's why we have this country called Liberia in Africa, because they had intended to send all these slaves back to Africa, liberate them, put them in a country called Liberia, We sent all these slaves to Jamaica, all these slaves to the Caribbean, right? I mean, they were going everywhere. And at some point they realized, yeah, okay, that's not going to work. Right? You think that we're not a racist society, we are. Right? In the 1800s, you would be hard-pressed to find somebody that wasn't racist. And we still, as evidenced by the current election, right, we're still basically a racist country. So those are the biases that we confront, right? And it's going to take an awful lot of work, I think, to get past those biases. At any rate, back to the task at hand. How did I get on Cope and Marsh? I don't know. All right, back to the task at hand. G. Evelyn O, because at the annual meetings of the American Society of Naturalists, he became president of the society, and in this presentation, basically his acceptance for this position was this. He published this paper called Homage to Santa Rosalia, and the subtitle is, what was the subtitle? Why are there so many kinds of species? And what he did, Santa Rosalia is this little church in Italy. He was there visiting, and Hutchinson was a specialist on diving beetles. And he goes into this pond, and he discovers that inside this pond there are all these different beetles, these diving beetles. And if you've ever seen diving beetles, they're kind of cool. They have these little boat-shaped bodies, and they have their back legs are shaped like oars, and they go diving down to the bottom to feed and so on. And in this pond, he discovered that there were 4 species of diving beetles. And even though we didn't have all those models yet for species coexistence, he realized that there must be some way in which these diving beetles are subdividing the resources. And he was trying to understand that. And he knew, for example, that big lizards eat big bugs and little lizards eat little bugs. And birds with big beaks eat big seeds, and birds with little beaks eat little seeds. He knew that these diving beetles must be subdividing the food resource somehow. So he collects all these diving beetles, and he realizes there are 4 different sizes. And he compares the size of the biggest one to the next one, to the next smallest, to the smallest. And he discovers that the size ratio is basically the same. It's about 1.4. So the biggest one is 1.4 times larger than the second biggest one. The second biggest one is 1.4 times larger than the next. And that one is 1.4 times larger than the smallest. And he goes, holy shit. Isn't that cool? The ratio is 1.4. In other words, these species are subdividing the resources based on, I mean, it's not probably the body size, it's probably the size of the jaws or something. But big beetles have big jaws, little beetles have little jaws. But that 1.4 ratio, now they had their first glimpse into how it might be that these species are able to subdivide these resources. And that set off this amazing period in ecology where people started going, holy smokes, let's look at lizards, or let's look at mice. There was this guy named Jim Brown, not the soul Jim Brown. Jim Brown, the guy with the high voice. Jim Brown is looking at these kangaroo rats and pocket mice in the Utah desert, and he discovers a similar sort of size ratio, only it isn't 1.4, it's 1.17. And another guy does it with birds and goes, yeah, no, it's 1.23. And another guy goes out and does it with lizards and says, no, it's 1.18. And somebody, No, it goes on for years. All these, what is the right ratio of one bigger than the next? Because really what they're doing is, all right, there's the biggest one, there's the next one, there's the next. They're figuring out that spacing. This goes on for years and years and years and years and years. So finally, there's this guy, and this always happens in biology. There's some guy who's just taken a biology class for grins and giggles, and he just needs something to amuse himself. You know, he's a mathematician or something, and he takes this biology class, and he goes, well, that's sort of amusing. Sees this ratio nonsense coming up, and he says, well, what would happen by chance alone? Let's imagine we were just to throw species at random in a community. What ratio would you find from biggest to smallest? And it turns out that you get basically the same damn ratios. So he does all this simulation work and replicates it again and again and again. In other words, there's no difference between the size patterns that you're seeing in nature and what you expect by chance alone. It's at that point where everybody throws their hands up in the air and goes, shit, and starts all over. Okay? Now, where we are today is at a fundamentally different place. Technology has improved rather dramatically. So now, using stable isotope analyses, we can look at a species and we can understand exactly what it's eating without ever looking at the stomach contents. We can, with an incredible amount of precision and detail, understand what these species are doing. So there's this sort of shift that's taken place in ecology. We've gone from synecology back to the way it used to be, which is odd ecology. Ecology. In other words, in odd ecology, you're looking at individual species. Here, you're looking at the system. So what most people are doing is they're going away from these huge, immense systems and concentrating on just interactions between one species and another. They're taking a simpler viewpoint, and that seems to be the most productive way, at least for the moment. All right, that's where we will stop for today. This week in lab, we want to do the data analysis for your forging stuff, and we're going to have another little exercise embedded in there, but we want to do that so that next week we can start the next sequence of labs on optimal forging. What I want to do next is talk about predation and forging. We'll probably start with optimal forging first to motivate your experiments, and then we'll finish up with predation. And by that time, I suspect it'll be time to shut down for the strict online part of the class, and we will at least have all of our field stuff out of the way. All right. Make sure when you come on Wednesday that you have your data. If you don't have your data ready, you'll just have to, I guess, partner up with other people so that you understand how the analysis is going to go. Good. See you guys next time.